Module 13C, we're going to start looking at X-ray diffraction, and so you can actually see how we can determine these crystal structures for solids. So I'll be able to explain why X-rays are used in XRD and determine the crystal structures of your solids. We do have 7 crystal systems that your crystals will be based off of. We've got cubic, tetrahedral, orthorhombic. I can't pronounce all of them. Rhombohedral, I think is how I say that one. I always mess that one up. Hexagonal, monoclinic, and triclinic. Within each of these, though, there are multiple other structures. So like for cubic, we have simple cubic, body-centered cubic, and face-centered cubic that we'll look at. Although we do have 7 crystal structures, we will only use cubic structures in this class. But again, within here, we have simple cubic, body-centered cubic, and face-centered cubic. So you need to know that there are 7 types of structures, and each can be expanded upon, but you are only going to be responsible for doing calculations with simple cubic, body-centered cubic, or face-centered cubic, which we do call BCC and FCC respectively. So how does X-ray diffraction work? Well, X-ray diffraction is a very powerful tool that we use to determine crystal structures. We can do this with crystalline solids or with powdered samples. What happens here is that we have X-rays that we are going to bombard a sample with. X-rays are very high energy. When I say high energy, I mean that the energy output on them, when I put the instrument through to actually start producing the X-rays, about 1% of the energy going through it is actually producing X-rays. The rest of it just generates heat. Very, very high energy. If you remember your electromagnetic spectrum, we saw that X-rays, we've got gamma rays, we've got X-rays. They're very high in energy compared to like radio waves, microwaves on the other end of the spectrum. What X-rays are actually doing is interacting with your electron cloud of the atoms themselves, and they're diffracted to produce a pattern. So we use, as chemists, physicists, scientists in general, we use computers to analyze the angles of diffraction and use this to determine distances and bond angles between the atoms. We can use this to determine exact 3D structures. So this is kind of what I'm talking about here. Sorry, didn't mean to hit that button. What I'm talking about here. We've got an X-ray source. It goes through, we do put it through lead. Lead is able to stop the X-rays, so lead we actually use to protect ourselves as well. These instruments are encased in lead, and there's other things in the glass and such to embedded into the glass and such that we can see the instrument running, but we're not harmed by it ourselves. But the X-ray goes through, it hits our crystal, and then it forms a diffraction pattern. We see that here as well. The system comes in, we have an X-ray angle come in, it hits our sample, and it's diffracted at a specific angle. The angle of these diffractions is measured, and these angles can help determine what system we actually have, what crystal structure we actually have. We can use that then to overall determine the overall pattern of the structure. So you've got a crystal, it diffracts, we collect data, we integrate that data, which is mathematical manipulation. We solve it and refine. And then we continue that process. We then continue that process. So we, took the crystal, we ran it through the X-ray. We see here, it diffracts, it forms this pattern. We collect that data, we integrate that data, so we apply, again, a mathematical manipulation to it. We solve that crystal structure, and we refine it and continue that process by solving and refining until we can actually see what we have, until we can actually tell, okay, this is the crystal structure we have. So here's some actual data from Dr. Fry when she was working on her PhD. I personally didn't work with single crystal. I did powder X-ray diffraction, which works slightly differently. Instead of finding perfect crystals, we just take a powder and we look at an X-ray pattern based on a powder instead. Slightly different application, same basic premise though, where we take a sample, We apply it, we hit it with x-rays, we watch the diffraction pattern, we see the pattern come out, we do a mathematical manipulation, and then we can backtrack and calculate to what we actually have. For single crystal, though, you do need to find the perfect crystal. That can be a very hard thing to do. You want the correct size, very clean edges, and it needs to be able to reflect polarized light. For people who do single crystal X-ray diffraction, a lot of their time is spent just finding the right crystal, growing the right crystal, elucidating the right crystal out of the mix. It's going to diffract, which is your strong reflections. Numerous spots mean good spots. So you see these lights on here, this is this diffraction pattern. We collect data. And is the data good enough to solve your crystal structure? We'll find out. We integrate that data, so you identify your unit cell, the space group, and the formula, and then you solve and refine it. By solving and refining it, you're utilizing your bond lengths, bond angles, and electron density peaks to determine the overall structure of that compound. You continue this process until the relative deviation between the observed and calculated is less than 2%. So you run it, you get data that looks like this, you start working on a computer to refine it, and eventually you solve your crystal structure.